CIA has initiated the service in corrosion management in 2010, Men of Indian industry with objective of creating awareness services to combat corrosion. This committee is headed by Dr. Baldev Raj, who was a former director of India Gandhi Center for Atomic Research and a famous personality in terms of corrosion and corrosion control, especially in the nuclear area. The Management Committee is a network of internationally renowned experts of corrosion who were committed to minimize corrosion-related losses. The activities are to provide solutions, directions, and guidance to minimize corrosion-related losses, corrosion audits, to explore possibility of corrosion regulation in India, help organize missions on corrosion at national and international forums, to spread corrosion awareness through training programs, workshops, seminars, publications, etc. Around 10 to 12 programs on corrosion management are conducted every year across India. To provide certification on corrosion prevention in order to build knowledge-based corrosion community, Corrosion Research Day celebrations on September 22, 2012 at Chennai. CMC celebrated first Corrosion Research Day also there. So far, 22 training programs have been held across the country. Nearly 680 organizations and 1560 senior and middle level managers and engineers benefited from these training programs. 7 corrosion audits have been conducted and solutions have been provided to the industries. 23 booklets on corrosion management. 23 booklets on corrosion management prepared. The current CMC expert strength is about 42. Some of the glimpses. These are some of the booklets which have been produced by CII Corrosion Management Committee. These are some posters which are there. Well, now coming to about me. This is essentially my contact details and other things which are given here. And of course, I'm thankful to management and staff of CII Avanta for organizing the program and providing all the infrastructure support. Special thanks are due to Mr. Sanjay Namdev, Ms. Priyanka Sehgal of CII Chandigarh for all the coordination. And I'm also thankful to CII New Delhi for webinar facilities. Special thanks to Mr. Suresh for local coordination. Well, my brief introduction. I retired as Additional General Manager NITRA, which is known as NTPC Energy Technology Research Alliance, the R&D wing of NTPC, in July 2012. By qualifications, I am MSc Electrochemistry with postgraduate diploma in corrosion science and technology from University of Ferrara, Italy. I am a member of NACE International, life fellow member of SIAST, IAAPC, and of course I am also a core member of the CII Avanta Corrosion Management Committee. I have over about 30 years experience in corrosion analysis, monitoring and control in power plants, 5 years with BHL R&D, then 30 years with NTPC, and now since then I am working as a freelance consultant in the areas of corrosion and water management. My specializations are corrosion assessment, failure investigations, corrosion monitoring, corrosion audit, design of cathodic protection systems, for underground pipelines, condenser water boxes, RCC structures such as cooling towers, etc. Selection of anti-corrosive coatings, development and implementation of cooling water treatment, wastewater recycling and treatment, chemical cleaning of condensers, boilers, pipelines, PVC film type filled packs of cooling tower, etc. Material selection, water management, research studies on extraction of moisture from flue gases, ash mineralization by flue gas, etc. Now, check it again. Well, now coming to the topic of today, corrosion management of industrial cooling water systems. Okay, this is broadly the content. Introduction, cooling water system problems, scaling in cooling water systems, fouling, biofouling in cooling water systems, corrosion in cooling water systems, cooling water treatment, monitoring of cooling water systems. Let me put this thing that though since I have been with the power sector, so probably my examples will be more on the power sector, but the principles and the methodologies are similar for all industrial cooling water systems. Typically, when we talk, because maximum use of water is in power sectors, in that case, if you look at it, the basic thing is there is a heat source is there. From the heat flows, it goes to the steam generator. Steam is produced, which is passed on to the turbine, and from there, the mechanical work is done, is converted to the electrical output. We get the electrical energy, and the steam is then sent back to condenser for condensing and then recycling to the steam generator. And from there, it goes to the cooling system, which is also the heat sink for the thing. If you look at it, the general efficiency wise, the total thermal input, if you look at it, is something which is in the red color that you see. And then in the yellow color, what you see is the net electricity generation out of that. Blue color, what you see is the heat losses on account of cooling water system. And then the gray color, what you see is the other losses in terms of the boiler flue gases and other thing. Now, if we look at this thing, the UN estimates that by about 2050, half the world's population will live in nations that are short of water. Water is needed, of course, for everything, energy sector at each step, energy extraction and production, refining and processing, transportation, storage, power generation itself. It is estimated that water consumption to generate electricity will more than double over next 40 years. Now, if you just look at it, average global water footprint is about 1385 meter cube per hour. In USA, it is about 2,842. China, it is about 1,071. India is about 1,089, which is less than half of what is there in USA. For a daily vegetarian diet, about 1,500 liters of water is required. For a daily non-vegetarian diet, about 3,400 liters of water are required. People will be probably surprised to see these figures. These are what is known as water footprint. Simple thing like a cup of tea, which is about 200 ml, it requires about 32.4 liters of water. Similarly, about poultry or the beef, you look at about is 15,000 liters. One glass of milk, it will take about 200 liters of water. So what does it mean? It does not mean that directly that 200 ml water is as such. It is essentially right from the beginning of the say growth of the tree plantation, milk generation, then water, everything taken together, sugar, all taken together, we take about 32.4 liter to make a 200 ml of cup of tea. Similarly, for eggs, another thing, about 404.7 meter cube per kg of egg are required. For cheese, it is about 5.3. For fruit, say about 1 meter cube per kg. Likewise, this is what is known as water footprint. And why we are talking about this thing? Because in today's scenario, this has become a need of the hour, and it is also going to be a mandatory requirement as per the national water policy, where the industry will be required to measure the water footprint of their industry and then report it in their annual report. What is the water footprint and how, what kind of efforts they are making in reducing this thing. And cooling water takes the maximum of the water. From the energy sector, if you look at it, the coal side, it takes the maximum amount of water. Wind takes the least amount of water. So that is where thermal power plant, they play the major role in terms of water consumption. What you see here, there are two charts are there. One talks about blue color, which is the water that is used, and the red color, that is the water which is consumed. That means that water which does not come back to the system. Now if you look at this map, Indian territory about 328 million hectare, 2.4% of total land area, 17% of world population, 18% of world's cattle population, and just about 4% of world's water resources. And what you see here, regions, red color with the multi-pronged drought area, blue color, low stresses, green color, high stresses. That means areas where the demand is very high and the water availability is low there. The total water that is consumed in the industry, almost 88% is taken by thermal power sector, which is about 88%. All other industries, they constitute rest about 12%. If you look at the water demand and supply, we are always short of the availability point of view. We will not be able to meet the demand unless until we do some drastic measures. Now these two charts, what you look here, it shows two things. As far as the water usage is concerned, power generation competes with irrigation, because power generation takes about 38% of the water requirement, irrigation takes about 39%. But as far as the water consumption is concerned, power sector takes about 3% and irrigation takes about 82%. Mainly because from the irrigation side, the water does not come back. If you look at the water availability point of view, for the energy sector, only just about 130 billion meter cube of water will be available by 2050, which will not be sufficient to meet the power requirement of the country. Now this is maybe slide may not be too much visible to you, but what it says is it is the total power generation, which is roughly about 2,30,000 megawatt, and out of that the major share is about 1,56,000 is the thermal power sector. And as I said already, the thermal power sector, that is the maximum user of the water in amongst the all industries. Typical water cycle in a power plant, 500 megawatt. This is the quantum that you see from the uses in different sector. This is sort of per capita or per megawatt, what is the water consumption for different kind of power plant which is there. This is something which was optimized recently with CA, and you see about 50 cubic of water will be available for 2 into 660 megawatt units, whereas for 500 megawatt till now it was about 33 cubic. So you can see already whatever the optimization was possible, lot of things has already been taken care and optimization has been done in terms of water utilization. Now, the figures that you see in red color, those are the figures of power that would be added, and that in thermal sector, that which will require about 34 lakh meter cube of water per year, per hour. So this much of water, you can imagine, will be very difficult to obtain, and you know the power sector is an important thing here, because for all utilities or the all industry, power is the backbone. If the power is not available, industries probably will not be able to run so quick, fast, or so efficiently. Now coming to cooling water. Typical cooling water system that you see, if there's a cooling tower, there's some additives are there, heat exchangers are there, there's a process is there, the process can be anything. It can be a power sector, it can be a chemical sector, it can be steel, it can be cement, anything can be there. Typical where nowadays, because this is going to be one of the requirement now, the upcoming thing is usage of municipal treated sewage water as cooling tower makeup water. So typical cycle for that which is there. Well, the water is basically used as a heat transfer medium and also as the final point to reject heat into the atmosphere by evaporating inside cooling towers. Cooling of water is an essential process at power generation and industrial plants. The most important uses of cooling water include condensing, turbine exhaust steam, cooling process fluids, protecting high pressure pump bearing, etc. Control of cooling water chemistry is very critical in preventing corrosion, scale, and fouling. The sources of water which are normally used are groundwater such as wells, bore well, springs, or surface water like lake, pond, reservoir, river, canal. Likewise, seawater including brackish seawater, estuarine, or the brackish water. Typical impurities which are seen in water are bacteria and viruses, microorganisms, turbidity, color, minerals, metals, dissolved gases, ammonia, organic matter, or various pollutants. Now this particular thing, why I have separately pointed out, that is the insoluble organic matter. Insoluble organic matter, that is the one which is nowadays causing a lot of problem, and in fact this is going to be a problematic area when we talk about using municipal treated sewage water as a source for the cooling water. It covers debris of vegetable and animal origin, microorganisms, oily material, humic material. The soluble organic material consists of humic matter, fatty acids, nitrogenous matter like protein, peptides, amino acids, etc., saccharides and sugars, dissolved organic gases such as methane, soluble extracts of vegetable and animal matter, synthetic organic compounds. Well, in general, if you look at it, river water collects dust and gases from the atmosphere. Surface water during movement on the surface of earth collects more of suspended solid, dissolved and volatile metals which may be organic or inorganic in nature. Underground water is in contact with soil formation and dissolve more minerals and salts. Suspended solids are likely to be less in groundwater as the subsurface porous soil acts as a filter. Water quality depends upon catchment area, conditions in the case of runoff, and mineral rock formation in the case of groundwater. Water quality from storage reservoir appears to be good as suspended solids settle down and upper layers are exposed to more aeration. As more nutrients are available at the bottom of the reservoir, they may stimulate the algal growth. However, rubbish from the town, fertilizers and pesticides from agricultural fields, domestic and industrial effluents may join any water course and completely change the water characteristics. Therefore, depending upon the nature of contaminants or impurities in water, they may be classified according to their characteristics: physical, chemical, bacteriological, suspended, colloidal, dissolved, organic or inorganic, mineral salts or toxic chemicals. Now, physical impurities, what are those? Color, taste, odor, suspended solids, turbidity, temperature. Chemical impurities can be pH, acidity, alkalinity, hardness, TDS, chloride, sulfate, nitrate, phosphate. Toxic chemicals, it may be inorganic like zinc, copper, lead, arsenic, cadmium, chromium, especially chromium 6, mercury, etc. or various organic compounds like pesticides, carbon tetrachloride, vinyl chloride, cyanide, phenol, chlorinated hydrocarbon, etc. Dissolved oxygen 8 to 10 milligram per liter makes the water taste good. In fact, this is one of the major by which we see whether how much contamination is there of organic material in water. If the organic material contamination is large, that means the contamination which is consuming dissolved oxygen, in those cases what you will see, the dissolved oxygen will be depleting, and we can very well imagine that the organic or the inorganic compounds which are consuming the oxygen are present in the water. Bacteriological impurities can be virus, bacteria, protozoa, helminthic worms, etc. Now typically if you see, there are three types of cooling water systems. The simplest system is the once-through system, where we take the cooling water from a source, maybe river, maybe lake or anything, pass it to the steam condenser, and then send the hot water is sent back to the main water body. That's one of the simplest system. But today, as per the environmental regulations, talk about, at least in India, that not more than 5 degree temperature rise can be there from the input to the output water which is coming to the water source. So which means now most of the things which are coming, they will be coming with a cooling tower, because necessarily it will be required to put a cooling source before it is passed on to the water body. Second system, which is probably a common system that we are aware, at least in our cars and other thing, which is the closed recirculating system. The car radiator and other thing, where we know there is a coolant is added, and that coolant keeps on circulating inside the thing, cooling the engine, but there's hardly any losses are there, because there is any loss, evaporations are less, there are no mickups are generally there. So generally the problems of corrosion and biofouling are observed there, and you use accordingly corrosion inhibitor or the biofouling control measures there. Third system, which is becoming the most common system, that is the evaporative cooling tower system. In this system, what we do is we take water from the source, use it for the cooling down the steam, and or any process also it can be cooled, not only steam, any other process also can be cooled, and that the cooled water are then passed on to the cooling tower, where they are cooled there, and then maybe some little makeup is there, and something is taken out as a blowdown which is sent to the effluent. Fourth category which is now coming up is the air-cooled condenser. Now air-cooled condenser, it does not require water as such too much. It works on the principle of the air coming in contact with the heated liquid and then cooling it down, and in turn that what heated thing is done through the atmospheric air, and the cooled system is sent back to the thing. Problem is, this is a very large system. If we compare all the three systems, one through cooling system, water withdrawal wise it is bad, water consumption wise it is okay, capital cost is also okay, plant efficiency is good, ecological impact is bad, because the temperature of the water which is going to the water body is generally higher than the input water. Evaporative cooling, water withdrawal wise it is okay, consumption wise it is bad, capital cost is okay, plant efficiency is okay, ecologically also it is okay. Dry or hybrid cooling, it is water withdrawal wise it is good, consumption wise also it is good, capital cost is high, plant efficiency is also low, and ecological wise it is good. In many cases, air-cooled condensers can have an effect of about 11% loss in plant efficiency if they are used, but it is something where you don't have water and you have to generate power or you have to run the industry and you require some cooling, then obviously air-cooled condensers are the answer. Now some of the terminology we need to understand, because these are regularly used terminologies, and people should be aware of these technology or the terminologies. Circulating water rate, that is the quantity of hot water entering the cooling tower. It is measured in terms of, say, meter cube per hour generally, or gallons per meter per minute. Ambient wet bulb temperature, the wet bulb temperature of the air encompassing cooling tower, not including any temperature contribution by the tower itself. Generally measured upwind of a tower in a number of locations sufficient to account for all extraneous sources of heat. Units are degree Fahrenheit or degree centigrade. Generally symbol what is used as a AWB. Approach. This is the difference between the cold water temperature and either the ambient or entering wet bulb temperature. Unit is again degree Fahrenheit or degree centigrade. Blow down is that water which is intentionally taken out from the system to maintain the concentration of various salts in the system. It is again measured in terms of circulating water. It is measured in terms of either meter cube per hour or gallons per minute. Cold water temperature, it is the temperature of the water leaving the collection basin, exclusive of any temperature effects incurred by the addition of makeup and or the removal of blowdown. Units are again degree Fahrenheit or degree centigrade. Counterflow, airflow direction through the fill is counter current to that of the falling water. Cross flow, airflow direction through the fill is essentially perpendicular to that of falling water. Drift is circulating water lost from the tower as liquid droplets entered in the exhaust air stream. Units are percentage of circulating water or GPM. Generally, this is something which is there, and many of the industries, they use drift eliminators, which reduce the effect of losses on account of drift. Because in the drift, what happens, along with the water, the chemicals which are used for the treatment, they are also taken away, and that means that there is a loss on both water as well as the chemicals which are used for the treatment. If you have good efficient drift eliminator, you can bring it down to 0.0001% or 0.0005% level, so which is achievable thing as per today in the industry. Dry bulb temperature, it is the temperature of the entering or the ambient air adjacent to the cooling tower as measured with the dry bulb thermometer. Symbols are degree Fahrenheit or degree centigrade. Entering wet bulb temperature, it is the wet bulb temperature of the air actually entering the tower, including any effects of recirculation. In testing, the average of multiple readings taken at the air inlets to establish a true entering wet bulb temperature. Units are again degree Fahrenheit and centigrade. Evaporation losses, because as we know, once the water is heated, there is some evaporation that takes place. Some water goes forms as a vapor and goes away, and that is what is known as the evaporation loss. Generally, this evaporation loss is something which is typical of the system and cannot be avoided. Fills, that is that portion of the cooling tower which constitutes its primary heat transfer surface, sometimes referred to as packing. Force draft, this refers to the movement of air under pressure through a cooling tower. Fans or force draft towers are located at the air inlets to force air through the tower. Heat load, total heat to be removed from the circulating water by the cooling tower per unit time. Units are BTU per minute or BTU per hour. Hot water temperature is the temperature of the circulating water entering the cooling tower distribution system. Units are again degree Fahrenheit or degree centigrade. Induced draft refers to the movement of air through a cooling tower by means of an induced partial vacuum. Fans of induced draft towers are located at the air discharges to draw air through the tower. Leaving wet bulb temperature. Wet bulb temperature of the air discharged from the cooling tower. Units are again degree Fahrenheit or centigrade. Liquid to gas ratio is the ratio of the total mass flow of water and dry air in a cooling tower. Units are LB or kg per kg. Makeup, is the water which is added to the circulating water system to replace water which is lost by evaporation, drift, windage, blowdown or leakages. These are measured in terms of the percentage of circulation water, and units are generally meter cube per hour. Natural draft. This refers to the movement of air through a cooling tower purely by natural means, typically by driving force of a density differential. Range is the difference between the hot water temperature and the cold water temperature. The units are degree Fahrenheit or degree centigrade. Riser is the piping which connects the circulating water supply line from the level of the base of the tower or the supply header to the tower's distribution system. Splash bar. One of a succession of equally spaced horizontal bars comprising the splash surface of a filled tank in a splash-filled cooling tower. Splash bars may be flat or may be formed into a shaped cross-section for improved structural rigidity and or improved heat transfer capability. When flat, these are sometimes referred to as slats or lat. Wet bulb temperature is the temperature of the entering or the ambient air adjacent to the cooling tower as measured with a wet bulb thermometer. Degrees are unit is degree Fahrenheit or degree centigrade. Wet bulb thermometer is a thermometer whose bulb is encased within a wetted wick. Now, different kind of towers which are encountered in the industry are forced or the induced draft cooling towers or natural draft cooling towers. Induced draft cooling tower or the forced draft cooling tower, there are fans are there and the air is induced or the force through that to cool the dropping liquid. In the natural draft, either it is a counterflow or closed flow, in either of the case, there is a natural movement of the air which cools down the hot water and then it is sent back to the basin and then back to the system. Normally these have a hyperbolic structures. Cross flow, counter flow type of thing. Cross flow means when it is across the thing, counter flow is when it is against the movement of the water. These are some of the things which need to be understood. As we said, evaporation. Evaporation is equal to the circulation rate multiplied by the differential temperature divided by 1000, where E is the evaporation rate, C as the circulation rate, and dt is the differential temperature between hot and cool circulating water. Drift is form of a blowdown that occurs due to entrainment of water droplets in the air leaving the cooling tower. Drift typically ranges from about 0.05% to 0.3% is the normal which was there, but today, as I said, efficient drift eliminators are there and you can go comfortably to 0.0005% of the drift of the circulation rate you can achieve comfortably. That means very low. That means even with a level of about say 80,000 meter cube per hour flow, you can have something about 4 to 6 meter cube per hour only is the drift. Makeup water added to the circulating water system to replace water lost from the system by evaporation, drift, etc. Cycles of concentration are those concentrations. If suppose we have X quantity of one particular chemical in the makeup side and in the outlet of the cooling water side, suppose it becomes 3 times X, then the concentration of cycle is known as 3. Blowdown is that water which we need to take out from the system so that the concentration of the solids are maintained in the system and the systems are not, it is in a balanced condition. So that is the blowdown that we give it. The total, if you look at the evaporation, blowdown, drift and makeup, the general relationship is C is equal to makeup of the flow rate or the divided by flow rate of the blowdown, or equal to blowdown of the fluoride, fluoride level of the fluoride or the blowdown magnesium level concentration divided by the fluoride concentration in makeup or magnesium concentration in the makeup. That will give us the concentration of cycle. Blowdown plus drift is equal to E by C minus 1, where the BD is blowdown, D is the drift, that is equal to E is the evaporation divided by C is circulation rate minus 1. Total makeup is evaporation plus blowdown plus drift. So these are the metric units for that. Calculations are a water balance diagram and on the system makeup is E plus D plus W. So then this is the derivation out of that, which says that if XC by XM cycles is equal to M by D plus W is equal to 1 plus E by D plus W. From a simplified heat balance diagram of this thing, this becomes C delta T Cp divided by Hp. Hp is the latent heat for vaporization, which is about 2260 kilojoules per kg. Delta T is the water temperature difference from tower top to bottom in degree centigrade. Cp is the specific heat of water, which is equal to about 4.184 kilojoules per kg per degree centigrade for normal water, river water or the fresh water. Windage losses W in absence of manufacturer's data may be assumed to be 0.3 to 1% of C for natural draft, 0.1 to 3% C for induced draft cooling tower, about 0.01% of less for the drift eliminators. But as I said, if you have a good drift eliminators, you can go to 0.005. Time per cycle, this is known as the time by which the one cycle of the circulating water completes, that is equal to the total volume of the system divided by the flow circulating rate or the flow rate. So V by E is given in meter cube per hour. This is the time will be in hours then. Retention time is, this is the oversimplified English, length of time for impurity to be removed through the bleed off system. For this application, the term bleed off means bleed off plus windage and other leakage losses and other things. This is given by the relationship V by B plus W. The bleed off is again in terms of meter cube per hour and T will be in hours. Half-life or holding time index. This is the time in which the chemicals present in the water, they will be reduced to their half-life, or alternately half of the water will be replaced by a fresh water. So that is what is known as the holding time or half-life time. This is calculated on the basis of HTI is equal to logarithm of V by BD plus D. ln is the natural log of 2. So this becomes about 0.693 divided by 0.693 multiplied by holding capacity of the system divided by blowdown plus drift. As an example, we have taken, suppose the system has a volume of 1000 meter cube and blowdown of about 280 meter cube per hour, and the drift is about 20 meter cube per hour, then the holding time industry works out to about 2.3 hour. We will discuss subsequently also what is the significance of this thing in terms of the cooling water treatment when we talk about it. There are three major water cooling application: wells and springs. They have a low suspended solid. Rivers and lakes are classified as surface water. They have high suspended solid and dissolved oxygen, low dissolved solid, etc. Seawater, brackish water, they have a high concentration of solids, and in seawater there is a very high level of chloride also. Conductivity is also very high. Types of impurities in water, generally they are suspended matter like turbidity, color, dissolved solids, dissolved gases like oxygen, carbon dioxide, etc. Then miscellaneous impurities are like bacteria, which require oxygen to produce carbon dioxide, are aerobic bacteria. Bacteria that do not require oxygen to produce hydrogen sulfide are anaerobic bacteria. That means bacteria which survive in presence of oxygen, they are aerobic bacteria. Bacteria which survive in absence of oxygen, they are known as anaerobic bacteria. Algae favors exposure to sunlight. That means even in your cooling tower, you would have observed the portion which is on the facing the sunlight, you will have more algae compared to the portion which is in the darker side. Fungi favors dark secluded areas. The common mineral substances can be present in 4 categories based on solubility. Calcium, magnesium compounds, solubility decreases when temperature rises, alkalinity increases, and available carbon dioxide decreases. Hardness salts are more likely to drop out at high temperature and pH. Sodium compounds are increase as temperature increase. If deposits with sodium are found, it can generally be attributed to extreme concentrations or evaporation to dryness. Bottom line is, sodium compounds are rarely a problem caused by the water treatment. Silica dioxide rule of thumb is solubility increases as alkalinity increases. Iron and manganese compounds rule of thumb are solubility decreases, the water alkalinity increases, and the degree of oxidation increases. For example, oxygen or the chlorine or bromine presence. Well, the objectives of a cooling water treatment program are to maintain optimum heat transfer in process equipment and heat exchangers, ensure equipment reliability and availability, minimize operating costs, provide predictive treatment recommendations of system operating changes and tower contamination, maintain healthy environment in moist areas around perimeter of tower, assure system conservation to keep all areas with fresh flow on a regular basis. Generally, the following problems are observed in a cooling tower: deposits of airborne solid particles, scaling, corrosion, biological fouling, wood deterioration, etc. So, proper operation of the procedure in chemical treatment can help us in controlling all these conditions. Airborne particles fouling, since it is cooling towers are open to air, airborne dust and debris can enter the water and eventually plug up the system. Strainers or filter will remove most of this material. They must be cleaned and maintained regularly. Common foulants: suspended solids, soil, sand, mud and iron. Airborne particles fouling, dirt and dust, process contaminants, for example oils, corrosion products, microbial growth, carryover, clarifier, lime, softener. Factors influencing fouling are water characteristics, water temperature, water flow velocity, microbial growth, corrosion, process leaks, and of course one important thing which is there in the industry, the airborne dust. That also constitutes a major source of fouling in the cooling water system. Scaling: common scales are calcium carbonate, magnesium silicate, calcium phosphate, calcium sulfate, iron oxide, iron phosphate. And the factors which affect the scaling, basically if you look at the scaling, is essentially precipitation of the dissolved solid at higher temperatures. So factors affecting scaling are solution pH, solution temperature, ionic strength, strength of iron, hardness ion concentration, hardness type, holding time index, treatment chemicals, phosphonate like phosphonate, polymer, phosphates, biocide, etc. Suspended solids. Biological fouling of the, this is of course becoming one of the major problems these days. It's a challenge these days. Recirculating is caused by algae, fungi and bacteria growth. The threat is uncontrolled growth of these organisms, which is enhanced by the warm water, abundant sunlight and the oxygen-rich environment found in cooling towers. These organic growths called slime can reduce flow rates in tubes, and channels can reduce organic acids and waste products that can corrode metals and can attack and destroy the wooden portions of a tower. Protection against biological fouling is of two types: mechanical methods such as trash bars and strainers, chemical methods kill the microorganisms, oxidizing biocides like chlorine, chlorine dioxide, bromine, ozone, etc. Non-oxidizing biocides, quaternary ammonium salts, etc. Typical corrosion reaction, if you look at it, in a corrosion reaction, basically it's an electrochemical reaction where the metal loses some electron and forms an ion. Now system is electrically neutral, so those electrons have to be accepted by some other body in the system, from where otherwise we will have a current flowing situation, which is something like what we see in the electricity. So in this case, there has to be a cathode, or the anode reaction. What we say is the release of the electron from the metal is the anodic reaction or the oxidizing reaction. Those electrons are accepted at cathodes. The reactions are where the electrons are accepted, and they are known as the reducing reactions or the cathodic reaction. Factors which influence the corrosion generally are pH, temperature, dissolved solid, system deposit, water velocity, microbial growth, etc. Typically, we see this is the kind of corrosion that we see, basic corrosion cell. Iron we have taken as a basic common example. Iron it removes 2 electrons are lost there, we get a ferrous Fe2 plus, we get it, and then the 2 electrons which are left there, they again in the oxygen present in water along with the electrons which are there, it forms hydroxyl ions. Now those hydroxyl ions will form a separate layer there, so that will change the thing that is known as the cathodic reaction there. For SRB, similar reactions occur. SRB is sulfate reducing bacteria, further we also will be discussing. Now typically these are the problems which are seen in a cooling water: corrosion, scaling, biofouling, fouling. Now corrosion is basically electrochemical reaction involving water and oxygen mostly. Scaling is the precipitation of the salts from the system. Fouling can be biological fouling or it can be inert fouling also. So in the biological fouling, it is caused by the bacteria or the macro species which are present there. Fouling is caused by the corrosion products, dust, or the treatment with chemicals which are used there. Typical thing that we see this, what you see here is the greenish product that you see. Like this one. This is a typical fouling that has been caused by the treatment chemicals. In this case, ferrous sulfate, which is dosed as a corrosion inhibitor in copper-based system in seawater. Now, same tube, if you see below, there is a severe corrosion has taken place. Because it was the glass tube, what you can see here is the DG implication also you can see localized attack on the tube. And because of this thing, then the tube starts puncturing and you start getting the condenser leaks. Typical problem that you see, you can see the severe crevice induced corrosion as well as different metal welding, galvanic corrosion you can see at the tube plate of your heat exchanger. That is the most prone area where the tubes are expanded and the small crevices are formed there in which the water goes there, and there is a differential cell is created in terms of either differential oxygen or differential concentration of chemicals, and you get the crevice corrosion there. Or because of the different tube sheet material and the tube material, you can have a galvanic corrosion there and you can have a severe corrosion there. Third thing that can be there is that area you can have a concentration of a microbiological fouling, and a microbiologically induced corrosion can take place all around that area depending upon the metallurgy that we are talking about. A typical biofouling in the river water system, what you see there, the picture that you see here, on top of this there was a calcium carbonate scale which was mechanically removed. So this is the condition we saw, and this is after chemical cleaning with the same tube. You can see a chain-like structure, but chain-like structure has been formed because of the microbiologically induced corrosion below the deposit. Typical fouling in the copper nickel tube because of the organic material. Then after cleaning, you can see the microbiologically induced corrosion below the deposits. This is the steam impingement plus ammonia attack on admiralty glass condenser tube. Normally, if you see, there is in the boiler side, we give a treatment of ammonia. Now that ammonia, when it comes to the condensate, it starts trickling down on the condenser tube, and if it is a brass tube, at the baffle point, it starts concentrating, and then ultimately it will lead to the corrosion of the condenser tube. That is known as the steam impingement, ammonia grooving. Typical microbiologically induced corrosion due to the organic fouling. Some more fouling. Now this is a typical case that you see. These are the stainless steel condenser tube which were transported through sea route, and either during transportation or during storage, seawater has ingressed into the system, and from the portion where the ropes were tied, these are the portion, and below that portion crevice corrosion took place and the tubes lost their thicknesses, and when they were tested, hydro tested, during hydro test, almost 700 tubes failed during the hydro test. Of course, tubes were replaced by the vendor, but commissioning time of about 1 year was lost. Now this is again due to a critical problem which can be seen towards the rivers which are there in the Himalayan region. So those like Yamuna River. So Yamuna River, when it comes down, along with that it takes some silt and some small pieces of stones also, which are hard material, and when they pass through the condenser tube, they do the erosion of the condenser tube by mechanically doing this thing. This is the typical calcium carbonate based scale. You can see a different composition. You can see somewhere the top layer is a fluffy layer, so that means it continued growing there. Some place you will see a glassy layer on top of it, which is an adherent layer. Now this was a typical case where the water was supposed to be corrosive in nature, but all of a sudden the plant reported they had a 1 mm thick calcium carbonate scaling. So when we analyzed the problem, we found there was a black layer, what you see on the top tube, that was caused because of the oil in the water. So oil formed a film that changed the heat transfer characteristics, and the water which was supposed to be corrosive in nature, even in that low scaling tendency also, a heavy scale had formed in a short while. So that is the outcome is we have to ensure that no oil comes in the cooling water system. Typical organically fouled tubes. This is a denickelfication of copper nickel tube because of microbiologically induced corrosion. You can see this is a portion, red color what you see. This is all the portion denickelfication has taken place. The nickel has gone out of the solution and the copper has replated on top of that. Typical corrosion and fouling in the CW system. Now this was a case, condenser scaling, calcium carbonate scale was there. The tubes had so much scale, the plant was losing heavily. They were not able to run the 210 megawatt unit to more than 150 megawatt, and then their vacuum and everything was dropping. So when we checked up, we were not able to put our fingers inside the condenser tube. So much thick condenser scale had taken place. So we chemically cleaned it, and that is what we gained out of that, almost 15 crore per annum. The plant gained, and they were able to operate the units full load even during the peak summer also. But chemical cleaning is just like an antibiotic. It is not the solution. Solution is you must have a proper water treatment so that this problem does not occur. Chemical treatment is only antibiotic as a type of thing. When you have come to that level where there is nothing left, then you do the chemical cleaning. Typically in a seawater system, it also got scaled because of certain operational problems. So there again chemical cleaning had to be resorted to, and we had a good amount of gain. Now this is a typical cases. These tubes, what you see, these are SS304 stainless steel tubes, which you can see a lot of corrosion product also inside, reddish color, what you see here. Now, this particular case, what had happened, the plant had a fly ash silos along the cooling water system. So fly ash used to fall inside the cooling water, and then it started choking the condenser tube. So below that, reducing atmosphere is created. So as we all know, stainless steels remain as a stainless steel so long they are in the oxidizing atmosphere. Moment the atmosphere is reducing, it behaves the same way as a mild steel system. So these tubes are steam welded tubes, and around 4,000 tubes at a time failed. So when we analyzed, that was the problem that we found. See, this is the kind of thing what you see, the fly ash mounts inside that cooling water system. These were the tubes which were choked. You can see the fly ash inside the condenser tube, and when it was clean, you can see one place it was shining, at the seam weld there was a corrosion was there. This is the characteristics which change the which were changed by the fly ash falling into the water. You can see the alkalinity, conductivity, everything changing because of the fly ash falling into the cooling water system. Now this is a typical biofouling. What you see here, this is the cooling tower fill pack, totally packed. Water cannot flow through that, it is lost. Other places what you see a thick algae there. You can see the third picture what you see, the pipe inside there is a lateral growth is there. So you can see how much water then it can flow because the diameter has already reduced. And then apart from that thing, there's a frictional losses are there. Fourth also is again a typical biofouling where the because of that the flow also is reduced and the tubes are susceptible to the microbiological induced corrosion. Now what you see here on the left side picture, this is the reservoir, make a water reservoir of a cooling water system. The water that the water that was coming here had a high level of impurities, especially microbiological or organic loading. Because of this thing, a powdery green algae was formed on top of the reservoir and below. So this algae was aerobic in nature. So it took away all the dissolved oxygen from the top of the water, and below that anaerobic bacteria like SRP etc. they started growing and then started fouling the system and then causing microbiological induced corrosion in the problem. Likewise, the other two bottom pictures that you see, that's a thick foam that is formed because of the organic material produced from the two different kind of trees. One is the acacia tree, another is the casuarina tree. Their leaves, they were falling in the cooling tower and they contributed to so much generation of the foam, and the foam was so stable that it was not degenerating even after 24 hours. Typically you can see a microbiological induced corrosion and the fouling, and below that the whole cause in the pipeline because of the corrosion below that. Now this pipeline what you see here is a main pipeline which is supposed to supply cooling water to a 630 meter cube pump, but it was not able to deliver more than 450 meter cube pump due to the severe fouling and corrosion in the pipeline. Ultimately this pipe was replaced by HDPE pipeline. The problem was resolved. This is the same station. You can see the raw water pipeline also so severely bifouled. Some more cases of bifouling. Again, the raw water pipeline of the same station, earlier station, we can see what is the condition. We cut the pipe and we can see the bifouling inside the thing. This water was only 10 ppm hardness, 10 ppm alkalinity, but so severe bifouling. See, normally there are many modes of doing the cooling water treatment. Generally people adopt the means of employing some vendor to do the chemical treatment at their units or the industry. But what we have found, there is an advantage if we do our own cooling water treatment program development, because it has, in that case, the control is totally in your hand and it is not dependent on any particular vendor. Treatment program can be easily modified as per the change water quality or operating condition, which may be difficult with the vendor-based program. Residuals can be monitored and effectiveness can be correlated with treatment program. Vendors provide proprietary chemicals without disclosing the residuals or active content of the chemicals. There are no hassles of selecting a vendor every time, including technical specifications or chemical treatment program, etc. No. See, we get the advantage if we are operating the cooling water systems at a higher cycles of concentration. But the practical thing that has been seen is, in most of the systems, an optimized COC of about 5 to 6 is there. Beyond that, normally there is not much advantage that we get in terms of, because in that case we have to use a very high quality of chemical, high dosages of chemicals, and then controls become difficult. There is very little change in terms of the change in the blowdown, because normally the treatments are based on the blowdown and the drift. So if the blowdown is reducing, so there is very hardly change in the chemical that is to be dosed. So virtually 5 to 6 COC is the generally optimized thing. But some of the places you might be able to go even higher, because I know one of the stations where, as I said, 10 ppm hardness, 10 ppm alkalinity was there. That station, they are operating about 15 COC without any chemical treatment. But that is dependent again upon the station to station. This is the typical cycles of concentration that has been carried out, and normally what you see down below, regional saturation index in the red color, what you see there, I have put 2.91. Normally it is not recommended that we go beyond RSI of 3. Lower than 3 RSI are very difficult thing to be treated by chemical treatment. We have to then go for the softening and other thing, this thing to operate on that. This is what you can see, typically a cooling tower with say 80,000 meter cube circulation rate, and the blowdown and makeup rate that you can see, and you can see at different COC your total chemical consumption goes down. So even though probably you might be doing a higher dosage of chemical, but still you will be doing, that is an economical method of treating at that level. So you need to optimize your treatment program based on your site conditions and the COC that can be achieved properly. This is the cost in terms of the same thing, continuation of the same thing. You see the cost is reducing, and drastically, even at say 30 ppm, it is about say 10,000 rupees per day compared to about 5 ppm at about say 1 through system or 1.5 COC. Same thing if we are operating. So there we are putting about 11,631, and here about less than 10,000 we are spreading even at 30 ppm dosage. So that is what I meant when I say that your overall cost goes down. This is the cost of chemical per unit that has been calculated. Now this is the generally acceptable levels of dosages that are given there. HEDP, which is again a common scale inhibitor, you can at the RSI of 6 to 5.5, you can go to 0.2 to 0.5, 5.5 to 5, you can go to 0.5 to 1.2. Similarly, 0.5 to 4 RSI, you need to do between 2.2 to 3.2 ppm of HEDP. Similarly, with the polyacrylate, which is used as a dispersant as well as antiscalant, you can go up to this thing 4.5 to 4. Polyacrylate is not a recommended dispersant or the antiscalant. Typical residues which are seen, but normally in a vendor, most of the vendors may not be able to give you what is the residual level, what is the active concentration there, because of their proprietary nature of the chemicals. See, for stainless steel, that is one of the things which is said that your water should not have chloride. If your stainless steel is 304 or 316, not more than 500 ppm, you can go up to. For 304, it is only 200 ppm, less than 200 ppm, but up to 316, you can go up to 500, and beyond 500 to say about 1000, you can go to, up to 3600 ppm, you can go to duplex alloy 2205. Beyond that, if you have the chloride level, then you can go for 6% moly super osmotic super duplex stainless steel. See, this is the tentative guideline that we had developed for operating with a seawater system. Cycle of operation, cycle of concentration 1.2 to 1.6, maximum 1.7, preferably less than 1.3 if we are not dosing anything. If you are going beyond that, that means we have to do the chemical treatment of the seawater also. Alkalinity should be about maximum 225. Skin temperature not more than 65 degrees. Below 50 degrees normally the acceptable range. Flow velocity not more than 2.5 meter per second. Of course, it will depend upon the erosion resistance of the tube metallurgy there. Something like titanium, it can go beyond 7 meter also as an erosion resistance, but then it will cause some other problems also. Reynolds number not more than 60,000. Suspension solid less than 8 ppm, or for fill type, or less than 15 ppm for splash type fills. RSI greater than 6.8 is preferable. Now this is a different kinds of scale inhibitors which are used commonly, HEDP, ATMP, PBTC. As the stress is increasing for the calcium carbonate to precipitate out, PBTC is one of the best things where at a very low level of dosage, it is able to control high level of stresses of calcium carbonate precipitation. Similarly, for phosphate, calcium phosphate stability, we need to maintain a pH below 8.5. If we are going beyond than 8.5, then we need to add special chemicals such as terpolymer or polymalic, etc., so that we are able to control the calcium phosphate stability. The calcium phosphonate, I mean, many times what happens, the treatment chemical anti-scalants like HEDP, etc., they themselves mix up with the calcium present in the water and then form the calcium phosphonate, which precipitates out as a calcium phosphonate. So again, that's a scale which is forming as a calcium phosphonate. So among the users of this thing, again, low levels of PBTC have been found to be more suitable where there is a possibility of the calcium phosphonate precipitation to occur. Zinc also, when we are adding as a corrosion inhibitor, if we are going beyond 8.5 pH, then we need to add stabilizers for the zinc to remain in the solution. Now this is what happens with the HTI. HTI, if it is suppose a common system is there where 3 units are connected together, or the 3 cooling towers are connected together, in that case, if all the 3 units are in operation, you get a very low HTI, which is given by the violet color. Yeah. In 2 units it is going there. But if it is a single unit is there, HTI is very high. That means your degradation of the chemicals is very fast, and you need to do higher levels of dosages to overcome the effect of the HTI. This is the stress feed and the HTI effect. Now, in general, corrosion rate in cooling water, it increases to about double with every 10 degree centigrade rise in the temperature. And for the normal cooling water application, the line that you see at 50 degree, that is suddenly there is a peak of corrosion is there. So that is the area which is the normal operating heat exchanger operating area, about 49 to 50 degree. So that time, that is the maximum corrosion is seen at that level. Effect of oxygen also, the rates at 40 degree or 22 degree, as I said, it almost doubles at every 10 degree. The effect of oxygen also, again, if the dissolved oxygen is present there, it continues there, and if it is the open system is there, then it starts dropping, because the oxygen will form a corrosion product which reduces the effect of the corrosion there. Thermal conductivity of different common this thing, calcium carbonate is about 2.6, and the biofilm, which is mostly consisting of water, and it is the saliva of the bacteria which is coming out. So that one has a thermal conductivity of 0.6. That means 1 mm thick calcium carbonate scale is equal to 500 angstrom thick biofilm, which is nothing but 90% is a water, and you can hardly see that thing. Only thing what you can do is, while touch, you can see a sticky layer on your fingers. That is what probably you will be able to identify. Typical effect of the biofouling. Typical test result of some station, particular problem where the problem was biofouling problem related. It was one through system, and at different level time period, when we analyzed, the microbiological characteristics were very high, much beyond than the acceptable levels, and because of that thing, the condenser vacuum was affected because the station was not using any chlorine or any other microbiological thing, because it was a one through system, large system, so they were not using any chlorine or anything. But when the problem started, after that they were advised to go in for the chlorine dosing, and then since then the problem is under control there. See, the chlorine is the most common biological control thing that is used there. In that one, the problem is beyond 8 pH, the effectiveness of the chlorine is less than 20%. So it is dropping out at that level. So we need to see what you are dosing. It needs to be supplemented if your pH is higher. Okay. If we look at it, there is a correlation between the ORP is oxidation reduction potential, which is the potential which is generated when the system is in equilibrium. So there is an oxidizing reaction, there is a reduction reaction. So that ORP measurement is a tool which can give you a direct indication in terms of the effectiveness of the biocide. Now in that case, even if you are maintaining 0.2 ppm free residual chlorine, and if the system is effectively working, you will get something more than 550 millivolt ORP. In a very good condition, you can get even up to 800 millivolt, but at least around 550 to 600 is a normal thing that you can expect in a good clean system. There are certain non-oxidizing biocides which are used, like methylene thiocyanate, organotin compound, quaternary ammonium salts, organosulfur, copper salts, DBNPA, etc. Normally what happens is this non-oxidizing biocides, generally they are used as a supplementing thing to the oxidizing biocide, and normally you are supposed to be doing an alternate type of biocides, because the bacteria, they get immune to the one particular kind of biocides. So say 2 weeks or 3 weeks, depending upon what is the system capability and the biocide capability, either in 2 weeks or 3 weeks you change to the different biocide, and then after another 2-3 weeks you come back to the original this one. Meanwhile, you continue supplementing with the oxidizing biocide like chlorine, which is the cheapest material as a biocide. Nowadays, one of the very effective thing is the chlorine dioxide. Chlorine dioxide is instantaneously generated gas, which is generated either from the chlorine water itself or through the acid, and it is much more oxidizing than the chlorine itself. And it has got much better stability than the chlorine. These are the 3 different reactions by which we can get the chlorine dioxide generation on the spot. For generation of the chlorine dioxide, we need a special generator to generate the chlorine dioxide. This is one generator which is used when we use the chlorinated water as the source for the chlorine dioxide. This is when we use a hydrochloric acid for generating the chlorine dioxide system. Now, if we compare the different biocides, oxidizing biocide, for a system with a clean system with a pH of 6.8 to 8, chlorine is the cheapest one, followed by sodium hypochlorite, and then costliest is the ozone. At pH 8 to 9.3, hypochlorite plus sodium bromide, they are supposed to be cheaper. Chlorine dioxide is a good choice there. Ozone again is the costliest one. For systems with high organic loading and pH 6.8 to 9.3, chlorine dioxide is the cheapest and the most effective biocide. Ozone is effective, but yes, costly, very costly. For systems with ammonia contamination and pH of 6.8 to 9.3, again chlorine dioxide is the cheapest and the technically viable thing. Okay. Many times these biocides are supported by biodispersants, which are generally say some kind of surfactant. So those things, they help in improving the efficacy of the biocide in attacking the bacteria and to kill them. And also it helps in cleaning the system also, because it helps in removing the dead mass from the system. Some physical methods are ultraviolet and ultrafiltration. Normally these are used in a small system, not in a very large industrial area. Fouling in situ films, cooling tower films, PVC films, the mechanical methods are filters for makeup water, side stream filters to remove suspended solid from the CT basin, CT air filters to prevent ingress of suspended matter. Chemical treatment along with the use of filters will reduce treatment cost. This is a typical side stream filter. This is a typical air filter for the cooling tower, but normally our places it will become too expensive, so people will not go for this thing. In this case, the entire cooling tower is encased in a filters, and all the air that comes through the cooling tower is first passed through the filter, and then it is again put a pressurized thing and sent to the cooling tower. So that makes the system very expensive, but yes, then it will take the system clean also. There are certain inhibitors which are used for fouling, like polymers are there, copolymers are there, terpolymers are there, homopolymers of polyacrylic, polymaleic, polysulfonic, PBTC, HEDP, etc. They are all common fouling inhibitors, as well as many of them have an anti-scalant role also. Corrosion in CW system. I think we are fully well aware how do we get iron. Iron is normally obtained from ores which are there in the nature, and then what we do is we put some energy, refine them, put milling, and then we get the steel. Now what has happened during the process, the material has acquired higher energy, and as you know that once you have a higher energy, the material will tend to go back to the least energy state, so that it becomes stable there. So the least energy stage is again the combined stage or the oxide or the sulfide stage. So the steel will try to react with the material or the oxygen or the chemicals in the surrounding area and go back to the compound stage, which is basically the backside to the ore side. So that means corrosion is a natural process, and it is a result of inherent tendency of metals to revert to their most stable compounds, usually oxides. And most metals are found in nature in the form of various chemical compounds called ore. In the refining process, the energy is put there, and so the corrosion is inevitable. Only thing what we can do is, by our efforts, we can control the level of or the kinetics of the corrosion to the extent which is acceptable for our process or the phenomena. Typical reactions which are involved is electrochemical, as I said, corrosion is an electrochemical phenomena. So metals, they lose electron, that's anodic reaction or the oxidation reaction. Their electrons are accepted somewhere else, so that is known as cathodic reaction or the reduction reaction. Typical reactions which occur in water systems. Again, how on the same pipeline also, how the anode and cathodes are generated, because there may be some variations in the surface condition of the pipe. So same pipe can become anode cathode also. At one point, another point it can become a cathode. Typical condenser tube plugging and condenser corrosion problem. Typical corrosion in the CW duct, walls, condenser water boxes. Now what you see here, this is the 40 mm thick plate which was punctured because of the seawater, and there is no coating, there is no further protection that has been provided. Even in RCC structure, there is a severe corrosion is there, and because of that thing, the reinforcement bars they start corroding, especially if they are in the coastal region. And because of the chloride and other thing, they start corroding. And once they start corroding, they expand the thing, and the entire concrete and everything falls, and the structure becomes dangerous. Like this, there is a crack that occurs. This is the column of the cooling tower. You can see the crack that has developed. So slowly, once it's there, it will lose the strength, and the cooling tower can fall also. Typical RCC structure. Now this is one of the method, cathodic protection, by which we can control the corrosion of RCC structures, especially in the coastal region. General corrosion, localized pitting corrosion, galvanic corrosion, or different forms are there. Maybe crevice corrosion, maybe you can have stress corrosion cracking. All those things are possible in the CW system. Systems which are generally affected are pipelines, condenser water boxes, tube plate joint, condenser tubes, internals, condenser tubes, external, inlet end of condenser tube, pumps, boiler tubes, carryover which is there from the condenser, auxiliary cooling water system, heat exchanger, plate, etc. Now this is typically what you see when we talk about, especially in a power plant. If you see the impact of the cooling water or condenser tube leakage can be seen. This is the normal river water case that you are seeing, and we have calculated the different amount of chemicals which can go to the boiler, which is having a high purity water as the treatment thing. So this is the kind of impurities which goes there in 24-hour or the 1-hour period. If you go to the seawater system, you can see there is a drastic change there, and immediately we have to take the corrective action once the problems of condenser tube leakages are observed. What are the causes of corrosion? Dissolved oxygen, dissolved and suspended solid, acidity or alkalinity, water velocity, temperature, microbiological growth, presence of CO, carbon monoxide, ammonia, H2S, carbon dioxide, chlorine, high chloride or sulfate, galvanic action, pollutants can be there, falling under deposit, falling or under deposit corrosion. The pH alkalinity was extremely important as it affects the corrosion significantly. As a general rule, corrosion potential decreases when pH increases. But as the pH increases, so does the potential for scale. What are the general corrosion control measures? You adjust the pH, effective aeration, effective chlorination, balancing the chloride and hardness, polyphosphate dosing, ferrous sulfate dosing for the seawater system, and having brass or the copper based system. Cathodic protection, corrosion inhibitors, correct design, use of corrosion resistant material, using anti-corrosive coatings, avoiding galvanic couplings, keeping the system clean. That's the important thing. Some of the important things are phosphates, chromates, zinc, triazole, phosphonates, molybdates. After that, chromates are generally ruled out these days because of the environmental considerations, and they are supposed to be toxic in nature, especially chromium 6+. Zinc is again a very good cathodic inhibitor, but there also being a heavy metal, the restrictions are it should not be more than 1 ppm in your water. Triazoles are generally used for the yellow metal, that means the brass, copper based systems. Phosphonates, they are very good cathodic inhibitor, and they lay down the monomolecular film on the metal surface, and in combination they are very good antiscalant as well as anti-corrosive, corrosion inhibitor. Molybdates, they are very good for this thing, but of course they are toxic, heavy metal, so use are limited, but they are very good corrosion inhibitor. There are certain nitrites which are used, especially in the closed water system, like your car coolant, that also contains nitrite based inhibitors. So the analytic type of these things are chromate, orthophosphate, molybdate, nitrite, orthosilicate. Orthosilicate, that is again considered suitable even for drinking water. Phosphate is again suited for drinking water where normal limit is about 5 ppm. Polyphosphate, zinc, polysilicate, polyphosphonates, they are all cathodic inhibitors. Monitoring can be done through corrosion coupons, corrosion rating, or water chemistry test. Cooling water treatment. Objectives are minimize scale, minimize corrosion, minimize fouling, minimize parboiling, maximum safety, maximum efficiency. It should be non-polluting. Water conservation has to be there. Scale control, calcium and magnesium compounds and silicates. Generally use of threshold inhibitors like phosphonate and or polymeric compound combinations. Corrosion control by using cathodic, anodic and absorption based inhibitors. Fouling control is through the metal oxide, cell and suspended material. Use of homopolymers, multifunctional copolymers or terpolymers, quadropolymers, etc. Microbiological control, biofouling and microbiological induced corrosion by use of oxidizing and non-oxidizing biocides and biodispersants. Threshold inhibition is the lowest level of chemical that can be used for treating the system in a particular system. So it should have a good calcium ion calcium crystal modification ability, stability with respect to oxidizing biocide, effectiveness in presence of metal oxide. Corrosion inhibition you can do by selective inhibitors by cathodic, anodic or complexing type. Passivity demonstrate better flexibility over precipitating type. Effective inhibitor stabilizer dispersants. Effective dispersants in presence of metal ions. Antifoulants are used for building synergy with antiscalants for threshold stabilization and calcium ion tolerance. Dispersing effectiveness, metal ion oxide tolerance. And for biodispersants, ability to detect sessile bacteria, dispersing ability, penetrating ability, and nonosity. Oxidizing biocides, they are used for stability over operational conditions, effectiveness over wide range of pH, oxidizing potential, corrosivity. Non-oxidizing biocides, they are selected effectiveness over different macrobiological species, algae, fungus, and various bacteria. Tolerance with respect to hardness, zinc, metal oxide, oil, hydrocarbon, etc. Compatibility with oxidizing biocides has to be seen. Retention time has to be seen. Inhibitory consideration has to be taken into account. Biodegradability has to be taken into account. Health, safety and environmental consideration, acceptable discharge level, biodegradability, handling issues, legenda effectiveness. Okay, these are some of the steps which we follow. So a typical cooling water treatment program may contain phosphate, trihexa, ortho, TSP, SHMP, etc. Organophosphate like AMP, HETP, PBTC, zinc sulfate, molybdenate as a corrosion inhibitor, triazole for copper, benzotriazole or TTA, dispersants, monoco or terpolymer, acrylate or sulfonate, malic, etc. for the dispersancy and antiscalant. Biodispersant for helping in the biocide and helping in cleaning the system. Biocides are used for controlling the biological problems. Generally for calculating the, because normally the pH is controlled at a certain level. To control the pH, what we do is we use sulfuric acid. This is the formula that we can use for calculating the sulfuric acid that is required per day in terms of the kg per day. Simply it is 0.026 multiplied by the circulating water alkalinity minus the alkalinity that we want to maintain. I have put 300 figure here, but whatever the alkalinity that we want to maintain, that I have to put there. So whatever the delta alkalinity that comes there multiplied by blowdown in terms of meter cube per hour will give you sulfuric acid kg per day that is required. This is a typical calculation for cycles of concentration and the acid that is required at different COC maintaining the thing. This is the typical cost of the chemicals which are used in the chemical treatment of cooling waters. This why I have put it here, at least you will be able to make out if you are using any program through a vendor, at least whether you are getting some kind of right program or not. Because if your total program cost is lower than the cost of the basic chemical itself, then I think you can imagine then what you are getting. These are the limits for the corrosion. Cleaning of heat exchangers and this thing, microfouling it is there, scaling is there, and normally online tube cleaning systems consist of like sponge ball system, brushes or different kind. They are run through the system and they are continuously running in the system and they keep on cleaning the tubes. These kind of systems are very good for the soft scale, sludges, biofouling. They are good. But if the hard scale is there, then they are not effective, because in that case they are not able to remove the hard scale. See, I have put something because nowadays many people come out with the non-chemical devices for scale control. There can be magnetic, electromagnetic, electrostatic, catalytic or mechanical. Different kind of thing which are available in the market. There is an electrocoagulation process in which through the electrochemical principles, the ions are separated out and then you get the proper treatment of that. Typical devices. But my comment is, most of the time these non-chemical devices have been found to be good for the smaller systems. Very rarely they have been found to be good for the big systems. Monitoring of cooling water systems. These are the typical guidelines which have been given by EPRI, US EPRI, Electric Power Research Institute, for the cooling water guidelines. So in that case, if you look at it, calcium not more than 900, calcium into sulfate not more than 5 lakh, M alkalinity 30 to 50 without scale inhibitor, 220 to 250 with suitable nowadays, but we can go up to higher pH, almost up to 9 pH we can go with a good quality of chemicals. Magnesium into silicate not more than 35,000, silica less than 150, total iron less than 0.5, total manganese less than 0.5. DOD, of course, here it is not mentioned in this one, but I put it in green. Less than 5 ppm BOD is a good measure for the water to be used, because this is now will be more required when we use the sewage treated water as a makeup to the cooling water system. Turbidity should be less than 2 NTU. Sulfide, if the copper based systems are there, should be less than 0.1. Chloride less than 200 ppm for SS304 and up to 500 ppm short duration and 500 ppm for SS316. Up to short duration even 3000 can be tolerated. These are typical microbiological limits. TBC, or the total bacterial count, should be less than 10⁴ CFU per ml, preferably 2 into less than 10⁻3. TFC less than 10 CFU per ml, SRB less than 100 per 100 ml, sulfur oxidizing less than 2, acid producing less than 100 per 100 ml, this thing that means less than 1 per ml, gas producing bacteria less than 1 per ml, nitrifying bacteria not desirable, ammonia producer not specified but not desirable, slime formers again not specified but not desirable, iron bacteria less than 2, manganese bacteria less than 2. I have given the protocol also by which they are tested. Cumulative corrosion rate of mild steel in a normal cooling water system should be less than 2 mpy with no pitting. General corrosion rate of stainless steel less than 0.1 mpy with no visible sign of localized corrosion on the access tubes. Corrosion rate of copper nickel less than 0.1. Same is applicable for brass also. Scale deposition less than 15 milligram per decimeter square per year. Total viable count not to exceed 10,000 counts per ml in cooling water. Complete microbiological analysis should be carried out once in 3 months. Sulfate reducing bacteria SRB not to exceed 100 organisms per 100 ml. Heat transfer not to vary more than 5% from the time of starting the treatment program. System should be free from deposits and fouling. System should be free from algae and fungi growth on towers, basins, sumps, etc. Scaling, Hard scale should not be there. Only scaling interests and loose in nature, which can be cleaned by water jet on deposit monitor, can be tolerated. Magnesium cycle to be consistent with cycle of concentration. Silica cycle to be more than or equal to magnesium cycle. These are the typical monitoring equipment monitored phenomena which can be seen: pH, calcium hardness, conductivity, copper, iron soluble or reactive, iron total, turbidity, then azole, orthophosphate, delta phosphate or delta orthophosphate, that means organic and inorganic phosphate, zinc, polymer, oxidizing bioxide, oxidation ORP, ORP is the written line, aerobic microbiological population count, sulfate reducing bacteria, adenosine triphosphate monitoring, ATP monitoring, that is a method by which again we are monitoring the microbiological matter. Carbon steel corrosion using C1010 alloy coupon, corrosion copper corrosion rate CDA443 alloy, stainless steel SS304 or 316, sludge and depth in tower basin, NASCO sludge or similar, basin water and this thing. But when we are using corrosion coupons, then it is a 30-90 days. Only thing is what we have to see is that will give a cumulative corrosion rate. It will not tell you instantaneously what has happened. So for that one you go for the online monitoring. Chlorine, low level continuous 0.2 to 0.5 ppm residual. Bromine 0.1 to 0.3. Only thing is, my question is, if anywhere there is a possibility of this water being used for drinking application, don't use bromine, because bromine is not accepted by WHO for the drinking water. Whereas chlorine or chlorine dioxide or ozone, they are all three are accepted in the drinking water level. Monitoring the cooling water, the various dosing levels for the non-oxidizing biocides. Monitoring has to be done generally every shift, at least once it should be done. pH, water level in sump, blow down rate, makeup water rate, temperature, residual chlorine, LSI or ISI is to be done, and then all hardness, alkalinity, etc. need to be carried out every shift. This is the complete analysis. Corrosion controlled by corrosion coupon, online corrosion instrument monitor, scale and fouling monitor to be used. Now these are the typical online monitors. This is a electrochemical based online biofouling monitor, which once installed in a system, there are what you see on the here, they are the electrodes. So these are the electrodes and they are at a slightly higher charge. So whenever there is a biofouling is there, first biofouling will occur on this one and you get the change in the current, and because of that thing you will know there is a biofouling change. So using this system you can optimize your biocide dosing. This can be fitted directly online or can be kept open in the cooling tower also. This is the combined online corrosion and fouling monitor. This is a typical laboratory cell that we use for the electrochemical assessment of the corrosion. This is a right side, what you see is a corrosion rate meter, and the left side what you see is the probe which can be fitted in the pipeline, and you can do the continuous online monitoring. But you can have this instrument also and have a laboratory probe and do the measurement of anything on a portable basis also. Typical corrosion rack as per IS 8188. Corrosion coupons, the circular coupons, I mean the coupons with the hole that you see, they are used for scale monitoring. This is way how we calculate the corrosion rate from the coupons. Typical biofouling monitor for the based on differential pressure, but I have my own doubts. I have never seen it working at any place. But most of the chemical supplier, they will have this differential pressure biofouling monitor. Dissolved oxygen analyzer, assessing corrosion, carbon steel less than 2 is excellent, 2 to 3 is acceptable, 3 to 5 fair corrosion, 5 to 10 unacceptable. Administrative guard similarly 0.2, actually it should be 0.1, now it has been modified to 0.1, and stainless steel again 0.1. Bacterial biological count 0 to 10,000, essentially sterile system. 10,000 to 5 lakh, system under control. 5 lakh to 1 million, system may be under control but should be monitored. 1 million to 10 million, system out of control, requires biocide. Over 10 million, serious fouling problem may be occurring, immediate biocide additive required. This is as a conclusion: monitor all parameters at the inlet and outlet regularly, use online monitoring equipment regularly, use proper chemical treatment with continuous analysis, use and optimize biocides and other chemicals. Wherever feasible, operate at higher COC with treatment. Water quality is not going to improve in future, that we have to keep in mind. Pre-treat the water followed by treatment for controlling scaling, fouling, corrosion and pipe fouling. Maintain cleanliness around cooling water system. This is the impact that I was talking about in terms of the holding time index. As your holding time index is increasing at the different COC, your treatment program becomes difficult, your chemicals start degrading very faster, and apart from that thing, as the temperature also increases, again the impact on STI is the same and we get the lot of degradation. Now last item of this series is the thing, that experimental thing that we had done, or development of online PVC film type films cleaning of cooling tower. Normally what happens is the PVC film type films, once they are there, they are prone to the fouling, and because of that there is a gain in weight. There is a gain in weight because of this, and after some time the efficiency of the cooling tower goes down, and because of the weight the entire structure goes down and you can lose a lot of thing. So this is the impact of microbes on the fouling. So basically this fouling what occurs is a combination of microbiological fouling and the physical fouling from the, mostly from the airborne dust. People have a feeling that it is the water related, but normally water side the problem is lesser. More problem, unless until we are no treatment, we have no clarifier, and we are using a direct water, then yes, it has an effect. Otherwise normally airborne dust has a more effect than the clarified water. As the fouling increases, tower performance reduces. This is a typical microbiological analysis of the fouling that was observed on different stations on the PVC films. You can see all of them are very high in level. See, this is the kind of thing. You can see this is thick algae. This is the fouled films. You can see the structure has deteriorated because of the weight. Because in this case, the 20 kg original fill pack weight had become 180 kg in about 6 months time. This is the kind of fouling which is there. It is mostly consisting of mud or dust or dirt, whatever is there in the system. So we developed this fouling method in the lab. We developed this thing. This was the kind of fill pack that we had received. We developed the method using hydrogen peroxide, and this is the clean film that you are seeing. Again, some experimental studies done with the chlorine dioxide. This was the received system. This is after using chlorine dioxide in a lab. But yes, since this is a lab thing, effectiveness was less. This is the kind of films that we had received. We tried to clean it with the HCl also. There wasn't much success. We tried with the high pressure jetting by putting the sheets on the cells there. So we got some improvement, but yes, not sufficient. This is the kind of fill packs that you see. They are removed and mechanically then cleaned. Because normally in the mechanical thing, what the people do it, they allow the fill packs to dry out, and then they, with some wooden piece, they beat it. So all the dirt and everything goes out. But in that process, the fill packs also get damaged because they are made of PVC. And then they become brittle and they break it. And after some time, then you have to replace the fill packs. So this is what was happening. We tried even with the soaking method using the chemicals. We didn't have much success there. This was the thing. There was hardly any foam there because it was done using a commercial biodispersant. It did not work so well. You can see some amount of dirt on the top of the foam. You can see, but yes, effectiveness was not that high. This is after cleaning, before cleaning and after cleaning of the fill packs. Then the online cleaning that we developed, it is based on linear alkyne benzene, saponate and a polymeric dispersant. Using this method, we have done the cleaning. This is a seawater based system, 660 megawatt, 5 units totally clean. You can see the cleaned fills. There was an improvement about efficiency improvement about 7.5%. Then freshwater fills, we have done 2 units. Again, second time again the cleaning has been done. This was the cleaning process. What you see, the foam is generated because of that, and that is the one which takes out the thing after putting the biocide there. So that removes the biological fouling, and the surfactant removes the dirt from the system. Very good improvement in terms of the vacuum. People who are aware of this thing, they will be knowing fully well the significance of this much of improvement in vacuum. So in this case, what we concluded is normal biodispersants which are having anti-foaming agent, they are not so successful, but the surfactant that we use along with the dispersant, that worked very well, and we were able to clean the systems pretty well. We need certain amount of foam, but yes, we have to be careful. We are not generating too much foam. Thank you very much. I think it's open to question.